Welcome to this lecture on complex trigonometric functions. Imagine you only know how to walk forward and backward on a straight line, representing the real numbers. On this line, sine and cosine are just repeating waves. But what happens when you are suddenly allowed to walk anywhere on a massive open field, representing the complex plane? Today, we will discover how these familiar waves behave when they are no longer trapped in one dimension, and how they unlock a deeper understanding of mathematics and physics. Now that we understand our goal, let us look at how we make this leap. In standard trigonometry, we think of sine and cosine as the ratios of sides in a right-angle triangle. But in the complex plane, you cannot draw a physical triangle with an imaginary side length. The geometry breaks down. So we need a new mathematical bridge to connect our old understanding of waves to this two-dimensional world. That bridge is the complex exponential function. Because we already know how exponentials behave with complex numbers, we can use them as a reliable foundation to redefine sine and cosine entirely. This brings us to the official universal definition of the complex cosine function. Conceptually, this formula comes from Euler's identity, which links spinning circles to exponential growth. In this equation, z represents any complex input, such as x plus iy. The symbol e is the base of the natural logarithm, and I is the imaginary unit. By adding a positive imaginary exponential and a negative imaginary exponential, the imaginary parts cancel out, leaving us with a pure cosine wave. If the imaginary part of z increases, the exponential terms cause the overall value to grow rapidly, which is a huge departure from real numbers. Similarly, we define the complex sine function using exponentials. This formula is derived by subtracting the two Euler equations instead of adding them. Here again, z is our complex input and e is the natural base. Notice the crucial difference. We are dividing by 2i, not just 2. That imaginary unit in the denominator is absolutely essential for making the math work out correctly and isolating the sine wave. Just like with cosine, if you plug in a complex number with a large imaginary component, the exponential terms will cause the sine function's output to explode in size. Before we move on, let us see how these formulas change our understanding of limits. In the real world, if you graph a sine or cosine wave, the function is bounded. It is permanently trapped between a ceiling of 1 and a floor of -1. However, in the complex plane, this rule completely breaks down. Because our new complex sine and cosine are built from exponential functions, and exponential functions can grow infinitely large, the trigonometric functions can also grow infinitely large. They are no longer trapped. If you feed them an imaginary number, the result can be massive. Let us see this unbounded behavior with a concrete example. We are given the task of calculating the cosine of the imaginary unit I. We want to see exactly what happens when we plug a purely imaginary number into the cosine function. We cannot use a standard calculator for this. Instead, we choose our new exponential definition of the complex cosine function. Our first step is to substitute z equals I directly into the formula. This sets up our equation with I times I in the exponents, which we will simplify next. Continuing with our calculation, we simplify the exponents. We know that I times I equals -1. So the first exponent becomes -1, and the second exponent, which already had a negative sign, becomes +1. We now have an expression with purely real numbers. By rearranging the terms, we see this is exactly the definition of the hyperbolic cosine of 1. The final answer is approximately 1.543. Physically, this proves our earlier point. By feeding the cosine function an imaginary number, we got a real output larger than the traditional maximum of 1. Now that we have evaluated a function, let us try solving an equation that is impossible in the real world. Finding a complex number z such that sine of z equals 2. We are given the output and asked to find the input. We choose the exponential definition of complex sine because it turns trigonometry into algebra. We replace sine of z with its formula and set it equal to 2. To isolate z, our first algebraic step is to multiply both sides by 2i, which clears the fraction and gives us a cleaner equation to work with. Continuing our solution, we need to deal with the negative exponent because it makes the algebra difficult. We do this by multiplying every single term in the equation by e to the power of iz. This clever step transforms our equation into a quadratic equation, hidden in disguise, where our main variable is the chunk e to the power of iz. We then move all terms to the left side to set the equation to 0. This now perfectly matches the standard quadratic form, setting us up to use the quadratic formula. Now we apply the quadratic formula to solve for e to the power of iz. We carefully plug in our coefficients. A is 1, B is negative 4i, and C is negative 1. Squaring negative 4i gives us negative 16, and subtracting 4 times 1 times negative 1 adds 4, leaving us with negative 12 inside the square root. The square root of a negative number gives us an imaginary result, which we simplify to 2i times the square root of 3. Dividing everything by 2 leaves us with I times the quantity 2 plus or minus the square root of 3. In this final step, we need to isolate z. We do this by taking the complex logarithm of both sides, which cancels the exponential on the left. The right side becomes a complex logarithm, which actually has infinitely many solutions due to the repeating nature of angles. Finally, we divide by I, which is mathematically the same as multiplying by negative I. This gives us our final answer. Physically, this represents the exact complex coordinates where the sine wave reaches a height of 2, proving definitively that such numbers exist in the complex plane. Now that we have used these formulas to solve problems, let us understand exactly where they come from. This proof establishes the foundational link between exponentials and trigonometry. We start with Euler's formula for a real number x, which states that an imaginary exponential is made of a real cosine part and an imaginary sine part. Next, we write the exact same equation but replace the angle x with negative x. Because cosine is symmetric or an even function, it stays exactly the same. But sine is an odd function, so the negative sign comes out to the front of the term. These two equations are our starting point for the derivation. To find the cosine formula, we simply add our two Euler equations together. When we do this, the positive imaginary sine term and the negative imaginary sine term cancel each other out completely. We are left with twice the cosine function on the right side of the equation. Dividing both sides by 2 gives us the pure cosine function written entirely in terms of exponentials. Finally, we take a mathematical leap of faith and replace the real number x with a complex number z. This gives the derived result for the complex cosine definition, showing exactly why the formula takes this specific shape. To find the sine function, we go back to our two original Euler equations, but this time we subtract the second one from the first. By subtracting, the cosine terms cancel out completely, and the sine terms add together to give us twice the imaginary sine term. We then divide by 2i to isolate the sine function on its own. Just as before, we replace the real variable x with the complex variable z. This gives the final proven result for the complex sine definition. The intuition here is beautiful. Sine and cosine are just symmetric and antisymmetric combinations of spinning exponential curves. Let us look at what this unbounded behavior actually looks like. Here you are seeing a three-dimensional plot of the magnitude of the complex sine function. The flat ground represents the complex plane, with the real axis going left to right and the imaginary axis going front to back. Notice the wave along the real axis. It oscillates perfectly between 0 and 1, just like the standard sine wave you are used to. But look at what happens as you move along the imaginary axis. The surface sweeps upward exponentially, forming massive steep walls. This diagram perfectly illustrates how complex sine retains its wave-like nature in one direction while growing infinitely large in the other. Why do we care about these complex trigonometric functions? Because in engineering and physics, waves rarely exist in perfect isolation. When analyzing alternating current or AC circuits, engineers use complex numbers to track both the size of a voltage wave and its timing, known as phase. Furthermore, complex sine and cosine allow us to model waves that are losing energy and dying out over time. This is exactly what happens to a Wi-Fi signal traveling through a thick brick wall. Even in quantum mechanics, particles like electrons are described by wave functions that rely heavily on complex exponentials. Without this math, modern telecommunications would not exist. We have covered a lot of ground today. Let us reinforce the most important ideas. First, complex trigonometry takes our familiar sine and cosine waves and extends them into a two-dimensional number system. Second, Euler's formula is the crucial bridge, allowing us to redefine these waves entirely as combinations of complex exponentials. Third, because they are built from exponentials, complex sine and cosine are unbounded, capable of reaching any value imaginable. You have now mastered the foundation of complex waves, giving you the tools to analyze real-world systems that decay, grow, or shift in phase. Excellent work.